All right, let's jump right into this explainer. Today, we are putting on two different hats. First, we're the aerospace engineer evaluating the gritty operational feasibility of lunar helium-3 mining. And second, we're the space investor evaluating the commercial returns needed to fuel the global energy market by 2030. If you've been tracking the fusion space, you know exactly how astronomical the stakes are right now. For our executive viability assessment today, we'll quickly flow through 1. The helium-3 appeal, 2. Lunar extraction feasibility, 3. Mark series engineering, 4. Thermodynamics and heat exchange, and 5. Logistics and commercial ROI. Section 1. The helium-3 appeal, solving the terrestrial energy crisis. Okay, the core physics here is absolutely crucial to understand. Fusing deuterium with helium-3 is an aneutronic reaction. What does that actually mean for us? It means the massive power produced is carried by charged protons, not neutrons. So you get virtually zero radioactive waste. Literally no toxic fallout, no induced radioactivity in the reactor walls, just a direct, highly efficient conversion of fusion power straight to electricity. And that brilliantly illustrates the immense commercial prize, a nearly infinite energy supply. To put this into perspective, just 1 million tons of helium-3 could yield roughly 7 times the energy humanity is projected to consume in the entire 21st century. It's the ultimate key to global energy independence. Of course, that's assuming we can actually go to the moon and harvest what the solar wind has been depositing there for billions of years. Section 2. Lunar extraction feasibility, overcoming low concentration regolith. So how do we actually get it out of the dirt? We basically have two core extraction methodologies to evaluate. On one side, you have the heavy machinery of mobile miners, and on the other, the in-situ heating of static domes. Now, static domes sound super appealing, right? Just place a massive dome over the regolith, bake it with microwaves or solar concentrators, and you don't even have to dig. But as engineers, we really have to look at the harsh material properties of the lunar surface. And the engineering reality heavily favors mobile mining. Why? Well, lunar regolith is an incredibly good insulator. It has terrible thermal conductivity. Trying to heat the surface from the top down without churning it up is highly inefficient. It's kind of like trying to bake a cake from the top down using a hairdryer. You'd be waiting hundreds of hours just to penetrate a few centimeters deep. Plus, the helium-3 is preferentially locked physically inside titanium-rich ilmenite, which is concentrated in the dark lunar Maria regions. So we literally have to dig up and actively agitate this specific dirt to release our fuel. Section 3. Mark Series Engineering. The Mobile Miner Blueprints. Enter our primary operational solution, the Mark III Mobile Miner Architecture. This isn't just science fiction. It's a rigorously modeled engineering blueprint from the University of Wisconsin. Doing a quick design review here, it relies on a massive 4-meter bucket wheel excavator out front, which feeds the fine dust into a central fluidized heating chamber and then stores the compressed volatile gases in those tanks at the rear. And it does all of this while crawling along at a slow, steady 23 meters per hour. The extraction itself is a highly specific 5-step thermodynamic process. The miner excavates, then performs physical beneficiation, which essentially filters out the large rocks so we only keep the microscopic fuel-rich dust. It preheats that fine dust, bakes it at 700 degrees Celsius, and finally separates the isotopic gases. But let's be real, operating heavy machinery like this in a highly abrasive vacuum environment with extreme temperature swings is a massive operational risk. That microscopic lunar dust is going to aggressively try to wear down every single moving part on this machine. And the scale is just mind-bending. 5 million tons. As an investor, this staggering number highlights your extreme risk. We're talking about moving 5 million tons of abrasive lunar dirt every single year, with just one miner to yield a mere 33 kilograms of helium-3. Now, yes, that 33 kilos is enough to fuel a 400-megawatt fusion plant for an entire year, but the physical infrastructure required to acquire it is absolutely monumental. Section 4. Thermodynamics and heat exchange. Optimizing the energy balance. The thermal process to release these gases is highly sensitive. The thermodynamics dictate that 700 degrees Celsius is the magic number. That's the sweet spot, where we release 86% of the trap's helium-3. But think about it. Heating millions of tons of dirt to 700 degrees requires an unbelievable amount of power. We are looking at around 82 megawatts of thermal energy if we don't recycle that heat. So, to optimize weight and prevent our power needs from totally bankrupting the mission, the Mark III uses heat pipe heat exchangers. Honestly, this is an engineering masterpiece. It uses a cascading series of hermetically sealed pipes filled with liquid metals, specifically mercury, potassium, and sodium, to transfer heat isothermally. The hot, processed dirt leaving the chamber transfers its heat directly to the cold, incoming dirt. This smart recycling achieves a massive 85% heat recovery. It drastically drops our thermal power requirement from 82 megawatts down to just 12.3 megawatts. Plus, heat pipes have zero moving parts, making them highly resilient against lunar dust. That remaining 12 megawatts of heat can then easily be provided by integrating large concentrating solar power systems that track the sun. Now, commercially, we have to look way beyond just helium-3. When we bake this dirt, we're releasing all the solar wind volatiles. The massive volumes of byproducts like hydrogen, water, carbon compounds, and nitrogen will actually end up subsidizing our helium-3 operations. Think of it like a silver mine where the bulk copper you dig up pays for the whole operation. Supplying future remote lunar bases or orbital propellant depots with these life support building blocks completely shifts the economic viability, making this incredibly attractive to space investors. Section 5. Logistics and Commercial ROI. Funding the ultimate supply chain. So, how do we physically deploy all this infrastructure by the 2030s? The biggest logistical challenge we face is landing these 50-ton miners onto the moon at an affordable capital expense. Legacy launch systems simply cannot deliver that kind of tonnage. Utilizing next-generation heavy-lift rockets like Starship is an absolute prerequisite to overcoming this bottleneck and scaling our production up to meet commercial deadlines. And the 2030 timeline is the critical factor here. Right now, private commercial companies are securing over $1 billion in capital to develop terrestrial helium-3 fusion reactors. They want these on the market by the 2030s. But those reactors are totally useless without fuel. The immense private investment currently funding fusion development absolutely must be matched by equal investments in space logistics and lunar infrastructure. The entire financial return of multi-billion-dollar fusion reactors is tethered directly to the success of this lunar mining supply chain. So I'll leave you with this provocative thought to consider today. With 2030 commercial fusion deadlines fast approaching, have we finally mastered the complex nuclear physics of clean, boundless energy, only to be held back by the financial courage needed to mine the moon? The blueprint is right here, the engineering is sound. Now it's just a matter of who is willing to step up and fund the ultimate supply chain. Thanks for joining me for this explainer, and I'll catch you on the next one.